It's my pleasure to introduce Stella Ocker, who is visiting us from Caltech and Carnegie Observatories, where she is a Brinson Prize postdoctoral fellow. Stella got her PhD in 2023 from Cornell, where she worked with Jim Cordes. Stella's research covers pretty much almost all scales relevant for astrophysics, from EU scales to cosmological scales. She works on pulsar scattering, fast radio bursts, ISM, and even physics of heliosphere with the Voyager data. Today, Stella will tell us about the electron density structure of the Milky Way. Please take it away.
Okay, thank you. Okay, so I'd like to start with my favorite astronomical image, and that is the Milky Way and H-alpha emission. So we see in this image that the galactic disk is filled with ionized gas that is structured across a vast range of spatial scales. We see dense H2 regions, wisps and filaments permeated throughout by the diffuse fluff that is the warm ionized medium. And this plasma isn't just confined to the galactic disk. It extends into the circumgalactic medium, where galactic outflows and intergalactic inflows meet in the baryon cycle that regulates galaxy evolution. And because this plasma acts as a foreground through which other phenomena are viewed, characterizing this distribution of ionized gas is essential to a wide range of astrophysical problems, including the study of fast radio bursts, or FRBs, which is one of my main interests. So I am interested in tackling this problem of how plasmas are structured using a range of both theory and observations covering different astrophysical environments and spatial scales. Here is an incomplete list of the observational probes that I use. For this talk, I'm mainly going to focus on what we learn about diffuse ionized gas in our galaxy from pulsars and how that applies to our understanding of extragalactic FRBs. But if you're interested in any of these other probes, I'm more than happy to talk about them. So galactic electron density models are not just useful, but actually required for a wide range of applications. Here I'm just highlighting 3 of the main applications for these models that I spend most of my time thinking about. The first and perhaps most obvious is that these electron density models are the primary source of distance estimates for compact radio sources like pulsars and FRBs. The second is that they are critical for foreground correction for extragalactic radio sources. So every FRB study that is ever published has to use a galactic electron density model to correct the effect of the Milky Way on the FRBs that we observe. And finally, these models are critical for defining the scope and strategy of radio surveys. These galactic models are actually directly used as input to define radio transient survey strategy. And you can see an example of this in the plots above. Here on the left, you can see the integrated electron density of the Milky Way predicted by the NE 2001 model. This is an all-sky map. And then on the right, you can see the observed distribution of electron column densities, or dispersion measures, versus galactic latitude for all radio pulsars and for FRBs. And so you see that for radio pulsars, all of their electron column densities fall under this nice cosecant curve, which is exactly what you expect for a galactic disk that has some characteristic scale height of ionized gas. And then you can see that nearly all of the FRBs that we know of lie well above this curve. And even at low latitudes, those sources are actually seen towards the galactic anticenter. So these FRBs are actually searched for by excluding all FRBs that have electron column densities below the expectation from galactic models. And so by definition, surveys like CHIME throw out any source that doesn't adhere to our galactic model's expectation for radio transients within or outside of our Milky Way. Now, of course, there are a number of other applications for these models that I could talk about, but I won't. So if you're interested in any other potential application of understanding electron density, I'm happy to discuss more. So the main observational tools that I'll talk about are the radio wave propagation effects experienced by compact coherent radio sources. So the first of these is dispersion. You may already be familiar with this. We see that radio pulses are dispersed in observing frequency versus time. In this dynamic spectrum, time is in units of pulse phase. And the time delay between different observing frequencies depends on the so-called dispersion measure, or DM, which is just the electron column density along the line of sight. The second main class of propagation effects that I'll discuss today is broadly referred to as scattering or multipath propagation. So radio pulses are scattered by electron density fluctuations along the line of sight, and this gives rise to a few key effects. The first is pulse broadening. This is observed in the time domain. We see that radio pulses become asymmetrically broadened as you go to lower and lower observing frequencies, and this is because scattered rays take longer to arrive at the observer. The second main effect is scintillation, so scattered rays interfere with each other at the observer, leading to a diffraction pattern that depends on observing frequency and time. Here you can see the characteristic signature of scintillation as intensity modulations in the radio emission we observe as a function of frequency and time. And then the last and most fundamental scattering effect is angular broadening. This is observed in the image domain. We see that what was once a point source becomes smeared out to some characteristic angular scale, where that smearing depends again on observing frequency. And so with these different observational probes, we can characterize not only the mean electron density, which is probed by DM, but also the spectrum of density fluctuations in the ionized gas. And so we relate these scattering observables to the power spectrum of density, which is given by this equation. Cn squared is the amplitude of the density fluctuation spectrum. Q is a wave number, which is inversely proportional to length scale. And then if these density fluctuations are generated as a passive scalar in, say, a Kolmogorov cascade, then the spectral index beta would be 11/3. And so all of these scattering observables can be related to the so-called scattering measure, or SM, which is the analog of DM, and that's just the integral of Cn squared along the line of sight. So the key point is that by combining these different observables, we can characterize not only the mean electron density structure, but also its fluctuations.
There is one more piece of information, which is part of the rotation.
Yes.
You didn't mention it.
No, I didn't. That's largely because I don't have time to, and also because I decided to focus on electron density structure. With Faraday rotation, you're sensitive to the product of the electron density times the parallel component of the magnetic field along the line of sight. So if you want to say constrain magnetic field structure, then you actually need to combine rotation measure with an electron density model of the galaxy. And so these models, which I'll talk about, are also used as input to construct magnetic field maps of our galaxy. But yeah, very good point. Okay, so the two most widely used electron density models today are called YMW16 and NE2001. You can see both of these models' electron density maps projected onto the galactic plane. And the model architecture is relatively simple. It involves analytic prescriptions for the electron density structure of different galactic components. So they include spiral arms, a thin disk, a thick disk, the galactic center, and specific local ISM features like the local bubble and the gum nebula. And NE2001 also includes a number of discrete clumps and voids, which are required to explain excess or deficit in DM and scattering along particular lines of sight. So one of the key things you'll notice in these electron density models is that they're very smooth, right? They don't have a lot of inhomogeneity in their overall structure. And the other main thing is that these models are calibrated using pulsar distances primarily, which are confined to, basically within a few kiloparsecs of the sun. So these are galactic scale models, but they are mainly fit using distances within regions that are roughly around here. Okay. So these two models are actually used interchangeably in the literature, but they are dramatically different. So here you can see the electron density of these two models integrated to 1 kiloparsec. And on the far right, you can see the fractional difference between the two. And you can see that for broad regions of the sky, the fractional difference between these two models is well over 100%. And this can lead to dramatically different predictions of, say, distances. So a substantial amount of work has shown that these models really do have room for improvement. And one of the ways that we assess this is by comparing the predicted distances for radio pulsars to their parallax distances. So here on the left, you can see a comparison that was done between parallax distances and model predicted distances. And roughly 30% of these independent distance measures are misestimated by both models by well over 1.5 times. And this is a highly line-of-sight dependent statement. So for some regions of the sky, the models misestimate distances by over 100%. Neither of these models is fully optimized for extragalactic studies. So neither of them include the CGM of our galaxy. And so in practice, if you're, say, performing an FRB study, you actually combine NE 2000 or YMW16's prediction for the ISM with a separate model for the CGM. And so on the right, you can see the DM contribution of the CGM for various models, which are largely based on baryon density profiles. And these models cover a fairly broad range. The green region is showing the range of DM that is consistent with FRB measurements. And one of the things we've seen over the past few years is that there are a growing number of very low DM nearby FRBs that are actually challenging our understanding of both the DM distribution for the CGM and in the ISM. And so a great example of this is the FRB nicknamed Mark, which was discovered by DSA 110. This FRB actually has a total DM that is smaller than the maximum prediction of NE 2001. So when it was first discovered, it was actually considered a galactic FRB candidate. But then it was localized to a host galaxy, which suggested that it was in fact extragalactic. And so this FRB really challenges not only our model of the ISM, but also the CGM. And so in practice, a new galactic electron density model should really consider these different components in tandem.
Got it. It's great. Okay, but I just have one question.
Yeah.
Which is, how many sources are used in those two models, the green and the purple?
Yeah, so I'm going to actually get to that right in a moment. Okay. So as I said, these models are primarily calibrated using distance measurements of galactic pulsars. There are a few different ways of measuring pulsar distances. I've listed those on the left. The gold standard of these methods is VLBI parallax. This plot is showing the distribution of all distances used to calibrate NE 2001 and YMW16. NE 2001 was calibrated using 108 distances. Just 14 of those were parallaxes. And YMW16 used 4 times more parallaxes. Now the situation looks different today. So here I'm now showing you the distribution of all measured pulsar parallaxes and globular cluster distances for pulsars, which are also very precise. And so today we now have a total sample of pulsar parallaxes that outnumbers all of the distances used to calibrate NE 2001 and is comparable to the number of distances used to calibrate YMW16. So many of these pulsar parallaxes were measured just in the past 10 years. And over the past few years, our discovery rate of pulsars and globular clusters has also increased thanks to really sensitive searching with Meerkat and FAST. And so just over the past few years, we've added 12 independent globular clusters to our full sample of pulsar globular cluster-based distances. So unfortunately, we do still need to rely on some of our less precise distance measures. One of these is H1 kinematic distances. So this is where we actually observe absorption features in the pulsar radio spectrum, and we use the radial velocities of those absorption features to infer kinematic distances. In practice, those only set bounds on the true distance to the pulsar, and this is by far the most imprecise method. In fact, the last catalog of H1 kinematic distances was published back in 1990 using a 1989 rotation curve. So this past summer, I actually worked with a Caltech undergraduate student named Steven Romero-Rees to compile a new catalog of about 70 H1 kinematic distances based on state-of-the-art rotation curves. And so you can see an example for one pulsar that we looked at here, comparing the results you get for 2 different rotation curves. Now, unfortunately, we still need these H1 kinematic distances because they are a relatively large fraction of all of the pulsar distance measures available. They also tend to probe the largest distances for which we can't obtain parallaxes. So we are actively working on developing a new galactic electron density model, and this model is really motivated by fundamental questions about the ISM. You can see an incomplete list of some of the questions that we're pursuing here. And the point that I really want to emphasize is that this is not simply an effort of recalibrating old models with new distances, in part because we have a wealth of data to mine from large-scale surveys of the multi-phase ISM, which really expand the range of problems that we can address in constructing a new model. And I'll give you an example of this in a few moments. So for the rest of the talk, I'm mainly going to focus on these first three questions. How do H2 regions and inhomogeneities in the ISM affect our understanding of electron density structure? And how are these related to variations in turbulence across the galaxy? And ultimately, these questions are really about constraining the ISM electron density structure at low galactic latitudes. And to motivate my focus on low latitudes, I want to first emphasize that at high latitudes, the electron density structure is already pretty well characterized. So here on the left, you can see the distribution of the perpendicular component of dm versus height above the galactic plane for all pulsars with parallax distances and pulsars in globular clusters, which are shown in blue. And this dashed curve and shaded region is showing the best fit plane parallel model for the electron density structure at high latitudes. And so this model gives you a best fit for the asymptotic value of dm perpendicular to the galactic plane. And here on the right, you can see a comparison between our best fit value for that perpendicular dm versus other models spanning the past 20 years. And so you can see that model inferred values for this dm are actually very consistent, even with increasing samples of pulsar distances. And so this really indicates that we've probably done about as best as we can in characterizing the electron density structure at high latitudes. We do see that there are some inhomogeneities at high latitudes. These are indicated by the outliers that are highlighted in color on the left. Some of these actually correspond to known structures like high latitude H2 regions, but overall we see that these are a small fraction of the full pulsar sample, which is actually very consistent with a smooth electron density distribution. Now, the situation really changes at low latitudes. These are where uncertainties in galactic electron density models are highly exacerbated, and there are a few key reasons for that. The first is pulsar survey incompleteness. So here on the left, you can see a comparison between the flux density of new pulsars discovered by FAST, which is the largest and most sensitive single-dish radio telescope in the world, compared to pulsars that were discovered by Arecibo and Parkes. And so you can see that FAST is really pushing down the flux density limit of new pulsars that are discovered. And this indicates a few key things. The first is that there are more pulsars out there to be discovered. The second is that these fainter pulsars tend to have larger dm and scattering than ever before. And so this means that the new pulsars being discovered are actually probing regions of the ISM that we simply haven't had access to with previous pulsar surveys. Now, the number of discrete ionized structures like H2 regions also increases dramatically at low latitudes, and this increases uncertainty in galactic models, which, as I showed you, assume a relatively smooth spiral arm distribution. So here you can see the number of H2 regions versus galactic latitude, and the number of H2 regions increases by several orders of magnitude as you get closer and closer to the galactic plane. And of course, this plays into our uncertainty in the location and density content of the spiral arms. NE 2001 and YMW16 both use smooth spiral arm models, but in fact, we know that the spiral arms contain many H2 regions. Here you can see a comparison between the spiral arm locations of NE 2001 to the most recent, I would say, state-of-the-art model for the spiral arm locations, and H2 regions with known distances are overplotted red. And so you can see that there are some dramatic differences between the spiral arm locations used in NE 2001 and our most up-to-date understanding of these spiral arms. And we see that the distribution of H2 regions is potentially more consistent with recent spiral arm models than with the model used in NE 2001. So moving forward, I'm going to talk a bit more about how crucial it is to incorporate H2 regions into a new galactic electron density model. H2 regions were long hypothesized to play a role in the distribution of pulsar dm and scattering. This actually goes back to one of the very first studies to try to predict pulsar distances based on an electron density model. But in fact, over the past many decades, only a few individual sight lines of pulsars with foreground H2 regions have actually been studied, and you can see several of those here. So we decided to change all that by doing a large-scale cross-match between known radio pulsars and H2 region catalogs. So we cross-matched the entire known radio pulsar population against 3,000 H2 regions with distance measurements. These were primarily based on the WISE catalog and a catalog put together by Hu and Han 2014. Here on the left, you can see an illustration of some of the H2 regions that were identified in the WISE catalog. So these H2 region catalogs are based on a combination of IR radio and optical measurements. So what did we find? Well, we found that H2 region intersections with background pulsars are actually far more common than previously thought. So here on the left, you can see, again, the distribution of pulsar DM versus galactic longitude for all radio pulsars at low latitudes in gray. And then the colored points are showing pulsars that were identified by our analysis as having foreground H2 regions. The blue and red points correspond to different impact parameter cutoffs for identifying an intersection between a pulsar line of sight and an H2 region. So we found about 630 intersections, and these also show a clear trend in DM. So these histograms are showing the fraction of pulsars at a given longitude, or on the right, DM, that have a foreground H2 region, and the majority of pulsars with high DMs have foreground H2 regions. And this is a pretty natural consequence of galactic structure. Most of these high DM pulsars are in the inner galaxy, where H2 regions are much more common. Now, the thin gray line in this figure is showing the maximum DM prediction of any 2001 integrating through the entire galactic disk at low latitudes. And you can see that there are several pulsars that have DMs far greater than that maximum prediction of any 2001. And what our analysis showed is that all of those pulsars have foreground H2 regions. So these H2 regions are a very natural explanation for pulsars that seem to deviate from galactic model predictions. Now, failure to include H2 regions in an electron density model can lead to substantial errors in distance estimation, unsurprisingly. So here you can see an example for the pulsar J1643-1224. And in the upper right panel, you can see the DM versus distance integrated through any 2001 along this line of sight. So the horizontal black dashed line is showing the observed DM of this pulsar, and any 2001 has to integrate to a distance of about 2.4 kiloparsecs in order to reach the observed DM. So it infers a distance that is actually twice as large as the observed parallax distance of this pulsar. On the bottom, you can see what happens when we try to include an H2 region along the line of sight using an internal density that is consistent with the H-alpha emission of this line of sight, which is shown on the left. So when we include a simple H2 region model, we actually can recover the true distance to this pulsar. So we also simulated the entire catalog of H2 regions, roughly 8,400, in order to see what the total contribution of a population of H2 regions could be to the electron density distribution in the galactic plane. So here on the right, you can see the result of a very simple simulation. We're assuming that all H2 regions have a constant mean electron density, and we're just integrating through all of the H2 regions along a given line of sight. So essentially, we're saying, what is the DM distribution if you have extragalactic lines of sight probing the full population? And so here again, you can see the distribution of pulsar DM versus galactic longitude in the blue points. And then the blue spiky curve is showing the result of our integration over all cataloged H2 regions along a given line of sight. And this curve is spiky. It goes down to 0 because not all lines of sight have H2 regions along them. So one of the things you can see is that for a very modest internal electron density of just 1 electron per cubic centimeter, we find that H2 regions can contribute the majority of the total electron column density for some lines of sight. The most dramatic example is for the Cygnus complex, which is right here. And then we also did another simulation where we allowed the internal electron density to be larger, 5 electrons per cubic centimeter, that's shown by the spiky purple curve. And so here this showed that if we were to modestly increase the electron density, then we could get H2 regions contributing as much as half of the total electron column density in the inner galaxy. But regardless, even for a smaller electron density, H2 regions can account for at least 20% of the total electron column density in the galactic plane. So this is a really clear indication that H2 regions have to be included in a galactic electron density model. And I want to emphasize that this is a really different situation than we were in, say, 10 to 20 years ago when galactic, the two most widely used models, were constructed. Up until now, it was basically assumed that H2 regions could be ignored in galactic electron density models because the pulsar population that was observed was so sparse that H2 region intersections were thought to be very rare. This is showing that we are finally reaching a point where the known pulsar population is large enough to actually probe populations of discrete structures in the ISM at scale. So this is really exciting. Now, it's unclear whether these H2 regions are also contributing to the distribution of pulsar scattering. Here on the right, you can see the distribution of pulsar scattering delays. This corresponds to the characteristic time delay of the asymmetrically skewed pulse, which is illustrated on the left. So here we have scattering delay versus DM for all radio pulsars with scattering measurements in orange. And then the blue points are the pulsars that were identified by our analysis as having foreground H2 regions. And so you can see again that the majority of high DM and highly scattered pulsars have foreground H2 regions. And again, that's a very natural consequence of galactic structure because most of these pulsars are in the inner galaxy. Now you can see that this distribution of pulsar scattering versus DM has this characteristic hockey stick shape. And this hockey stick shape, we think, arises from the fact that most of these low DM pulsars are probing predominantly the local ISM and the outer galaxy, whereas these high DM pulsars are probing the inner galaxy. And we think that there are some changes in the strength of turbulence between the inner and outer galaxy that can explain this change in slope between tau and DM. But this raises a bigger question, which is what is the proper way to model scattering on a galactic scale? What is the role of, say, a diffuse turbulence that permeates throughout the ISM versus discrete structures like H2 regions? And the canonical picture of radio wave scattering for the past several decades has been that scattering predominantly arises from turbulent density fluctuations across a range of spatial scales. Here on the right, you can see a schematic compilation of all of our constraints on the power spectrum of density fluctuations in the ISM versus wave number, spanning a really broad range of spatial scales. And these are from a combination of both in situ probes like Voyager and remote probes like pulsar scintillation and scattering. And so our canonical picture is that these density fluctuations give rise to scattering, and we see scattering variations across the galaxy because the amplitude of the turbulent spectrum Cn squared changes across the galaxy. Now, this picture may not be a totally accurate picture of the ISM. But one of the main ways that we've chosen to include it in galactic models is by using a so-called ionized cloudlet model where we treat the ISM as a composition of cloudlets that have internal turbulence following a Kolmogorov spectrum, which is usually a fair approximation of the scattering that we observe. And so here you can see the expression that relates DM to the scattering delay in this ionized cloudlet model. And the strength of the turbulence is captured by this composite parameter F tilde, which is essentially describing the strength of density fluctuations. But you can see here that it's proportional to the amplitude of the density fluctuation spectrum divided by the mean electron density along the line of sight and the dissipation scale of the turbulence. And so this is the overall picture that was used to predict scattering in NE 2001. But over the past 20 years, our understanding of scattering has changed, and that is largely due to observations of radio scintillation. So scintillation refers to the time variable interference pattern that is produced when scattered rays interfere at the observer and the observer is moving relative to the source. Here on the right, you can see a nice example for the pulsar B1929 plus 10. So here we have Radio intensity as a function of frequency versus time. Here the time scale is 2 hours. And so this variable crisscrossing pattern is the scintillation pattern, which changes over time as the pulsar moves relative to us. And so one of the main ways that we analyze these scintillation patterns is using Fourier analysis. So we take the dynamic spectrum, we take a 2D Fourier transform, and we get what is called the secondary spectrum. And what we see in the secondary spectrum is that the scintillation is actually all concentrated along these parabolic arcs of intensity. And we refer to these as scintillation arcs. Okay, so why are they parabolas? The parabolas are actually just a generic geometric effect. They are related to the deterministic relationship between scattering delay and scattering angle. So that's actually very simple and generic. What is more striking is that we see these arcs are very thin and highly defined. And it turns out that that means the scattering is concentrated to discrete localized regions along the line of sight. Every arc that you see in a secondary spectrum corresponds to a separate location of scattering. So we carried out a survey of scintillation arcs using FAST. Here you can see the full sample of secondary spectra that we measured from this survey. And one of the things you can see is that basically every pulsar we observed had scintillation arcs. So these arcs are very ubiquitous. And the key point is that they are probing angular deflections that are on the scale of microarcseconds to milliarcseconds. So the equivalent spatial scales of the density fluctuations that are being probed are much less than an AU to roughly an AU for a typical pulsar at kiloparsec distances. And one of the things that we've seen by studying very bright nearby pulsars is that there are actually way more scattering structures in the ISM than previously thought. So here you can see two of the most dramatic examples. On the left, the pulsar that I showed you before, B1929 plus 10, which we observed with FAST. And on the right, you can see another pulsar, J0437, which is actually the nearest millisecond pulsar to Earth. And you can see that in both of these cases, there are many, many arcs in the secondary spectrum. And this is remarkable because both of these pulsars have very low DMs and are very nearby. They are only a few hundred parsecs from Earth. And so this leads us to the very simple conclusion, which is that by taking the total DM divided by the number of screens, or distinct arcs, we see that the electron column densities of these scattering screens are actually very small. And so the structures responsible for scattering can be a very tiny fraction of the total volume of ionized gas along the line of sight. That's an interesting question. So we haven't considered protoplanetary disks. We have looked at whether, say, the astrospheres of stars could explain this. And it's really hard to get enough astrospheres along a given line of sight. So it turns out that like the rough density of screens that we infer from these two pulsars translates to a rough mean free path of screens of about 10 parsecs. Which is quite large. There are ways to finagle, say if you have stars that generate bow shocks, which may leave a much longer trail of enhanced gas. Maybe that could explain it, but it's pretty hard. And even more confusingly, like you can look at the distribution of intensity along any given arc, and you can actually compare that to what you would expect for, say, a turbulent screen. And you see, like for these two pulsars, that they are consistent with turbulence. So we have a combination, basically, of discrete structures that also sustain internal turbulence. And these structures have to be common. Another really interesting point about this pulsar on the right, J0437, is that these very, very shallow arcs are detected. These are shown in this zoomed in region here. Those are actually consistent with arising at and within the bow shock of the pulsar. So this is a pulsar that has a bow shock observed in H-alpha emission, and these screens are associated with that bow shock. And it turns out that that lets you do really amazing things like constrain the pulsar distance to within parsec accuracy, which is like wild, but anyway. Yeah, so this is kind of puzzling. Yes.
This is quite in line with MHD ISM turbines, what you would expect, right? I mean, there are highly magnetized vortices on very small scales. The dissipation scale and the polar diffusion scale, or something like that, is roughly of the order that I think you infer for these structures. So I think there is lots of small-scale structure that you also see in very detailed H1 polarization stuff, the stuff that Karl Heiss and Haberkorn is doing. So I think this all points towards the same direction.
Yeah. Yeah, I think you should be right.
I mean, you would not need to find discrete objects, I don't know, astrospheres or maybe protoplanetary disks. That stuff permeates the entire ISM relatively densely.
Yeah.
Ralph, would that be the same in the neutral and the ionized gas, the structure scales?
I think there is, I mean, these phases are often closely interdispersed, right? I think you often have not a clear separation. So yes, this turbulent stuff with different properties in the local bubble.
If that's the case, then with 21 centimeter data of pulsars, you can also see the same structures. Did anyone try that? 21 centimeter from pulsars, does it show the same structures?
So in some cases, yes, but in practice, it's very difficult to make those measurements. So we know of maybe a dozen pulsars that show H1 features that are consistent with arising from roughly AU to tens of AU scale structures that pass along the line of sight, right? So we see these H1 features come and go. These are referred to as like the tiny scale, ionized structures. And for this pulsar on the left, actually, you see those structures in the pulsar spectrum. And you see these scintillation arcs. But we don't actually have like concurrent enough observations to say whether they're related to the same structure. And that's actually something that I would really like to try to do moving forward, is like contemporaneous searches for H1, tiny scale structures and scintillation arcs, like in the same observation easily. That would be nice.
Could it be, sorry,
Yeah.
an interesting exercise to take very high resolution models of magnetized ISM turbulence and run your analysis in such a system? Because if the proposition that it is really, the dissipation scales within the turbulent ISM, you should find something that looks very similar.
Yes, so the short answer is yes. I absolutely would like to see that happen, and nobody has really done that yet.
Because we would not know how to analyze it, but...
Yeah. And of course, one of the challenges is like finding simulations that can reach like sub-AU scales. So if such simulations exist, then it should absolutely be done.
The second question is whether to trust them.
Yeah.
That is a question.
Sure. Of course.
Let's speak afterwards.
Yeah, please.
I have to stop it.
Yeah. Okay, so we have tried to synthesize the locations of scattering screens with larger scale features in the ISM to see if there's any relation between them. So here you can see an example of our attempt to do this. And so this is showing models of the local bubble based on dust extinction maps, the Pertau shell, the local super bubble. These spokes are showing different pulsar lines of sight, and then the black squares are the locations of scattering screens inferred from scintillation arcs. And so one of the things we see is that there are potential associations between some structures and scintillation arcs, like H2 regions, but overall there's no obvious correlation between the locations of scattering screens and larger scale features like, say, the wall of the local bubble. And so this, again, potentially points to a picture in which generic turbulence is a more appealing answer. But it's really a mixed bag, I would say. And so we're actively working on developing the methods to properly incorporate scattering in a galactic scale electron density model. This link will take you to the underlying source code for this visualization, and it'll continue to grow as we add more and more models of galactic structures and scattering screens. Okay, So I think it's worth explaining why an accurate model of galactic scattering is important, because I've harped on about scattering, but you might say, well, why do we even care? Especially if turbulence might just do a generic enough job. So I think one of the best ways to illustrate is to show what is clearly a bad approach to modeling galactic scattering. And this is the approach taken by YMW16. So here you can see, again, a schematic of the scattering delay versus the galactic DM. And from what YMW16 does is it simply uses this empirical hockey stick relation to predict the scattering delay of any given line of sight based on its DM. This is really problematic, especially when trying to predict the scattering of extragalactic sources like FRBs. So here you can see the distribution of scattering delays measured by the CHIME survey for catalog 1 versus the galactic contribution DM for all of those FRBs. And what YMW16 does is it basically just takes the galactic DM of these FRBs and it plops it into the hockey stick diagram, and it says, okay, this is what the galactic contribution to the scattering of these FRBs is, and that's shown by the red region. The problem is that this leads to scattering estimates for extragalactic sources that are off by several orders of magnitude. And this is because all of the FRBs shown here are actually viewed towards the galactic anticenter and at high latitudes, which corresponds to the lower portion of this hockey stick. But these are extragalactic lines of sight. So they probe the entire electron density column through the galaxy, which places them in the higher DM part of this hockey stick. And so this is very problematic because it can lead you to incorrectly infer that the Milky Way induces significant scattering along FRB lines of sight, and that for some of the highest DM lines of sight, the Milky Way actually dominates the total scattering that is observed. Okay, why does this matter? Well, it matters if you want to remove the galactic foreground contribution to scattering in order to learn something interesting about the extragalactic environments probed by FRBs. One example of this, which is a case that I've worked on, is using scattering to probe the circumsource medium of a repeating FRB. So this repeating FRB, 2019-05-20b, turns out to have scattering delays that vary significantly. So here on the right, you can see an example of pulse signal to noise versus time in milliseconds for one particular burst in blue. And the best fit model for this burst, including a scattering delay, is given by the orange curve. And then this green shaded region is showing the range of scattering delays that we measured from other bursts from the same source. And so we detected that the scattering delay can vary by over a factor of 2 between different bursts. And in fact, we inferred that these scattering variations could happen on timescales as fast as minutes. This corresponds to length scales for, say, density clumps that might be associated with the scattering variations that are less than 0.4 AU in scale size. And so we think that these scattering variations are coming from the circumsource medium of the FRB. You can see one possible schematic of a model for FRB progenitors in which you have these layers of shocked and ionized gas. And so this scattering is potentially coming from a layer that is very close to the central engine of the FRB. Now the issue is the Milky Way also induces variable scattering. So we see from pulsars that scattering can change over time scales, but now time scales on the order of months. And galactic electron density models can give you a prediction for what the scattering variability will be along a given line of sight. And so if you're not careful in your galactic modeling, then you might basically fail to properly interpret the scattering variations of any given repeating FRB, which prevents you from learning something interesting about its circumsource medium. Another example of why galactic foreground modeling can be important for scattering is an example that I'm showing here. And this is actually an attempt to use scattering to place some constraints on turbulence in the CGM. So here this plot is showing the strength of density fluctuations, which is parameterized in the cloudlet model I showed you earlier. So this is density fluctuation strength versus the dissipation scale of turbulence in the CGM. These colored regions are showing the predicted level of density fluctuations based on quasar observations of turbulence at larger spatial scales. So it turns out that the quasar observations give us some inference of what the strength of density fluctuation should be. And we actually compared that to an FRB scattering upper limit based on work by Liam Connor, and that is shown by this horizontal black solid line. And the point is that by combining an FRB scattering upper limit with quasar observations of turbulence, you can actually place bounds on the scale of dissipation in the CGM. Now, the issue is that this FRB upper limit is roughly on the order of a nanosecond time delay. And so at this very tiny level of scattering, you really need a robust estimate of the galactic contribution. Okay, so moving forward, we are working on developing a new model. The first step in this was a fully Python version of NE 2001, which was essentially a test bed for starting to construct a new model, in part because NE 2001 was based on Fortran. Going to a model based on Python involves significant slowdowns, and so you have to pursue alternative computational approaches to building these models. So here's a link to the Python version of that package. And right now, we are actually working on essentially testing like a sandbox for modifying the model by including H2 regions and modifying the thick disk. So we're currently in the phase of kind of playing around, and we're going to release an extension to NE 2001 later this year, which will include some of our modifications. And this is all on the road towards developing a completely new galactic model where all of the components will be revised based on the most up-to-date distribution of pulsar distances, DMs, and scattering, and based on including data from other surveys of the ISM. So the main point I want to emphasize is that this is really the right time to do it because the number of robust pulsar parallaxes today is comparable to the number of all distances used to calibrate these older models, most of which were not actually parallax. And over the next few years, oh yeah.
Sorry, yeah, just on the previous slide.
Yeah.
The question is there a reason you're kind of using the NE 2001 model as a baseline to modify versus the other one?
Yeah, I mean, it's honestly personal bias. Jim Portis was my PhD advisor. So I'm the most familiar with that model. I did the translation to Python. I went into the weeds, dissected the whole thing. So it's just what I'm familiar with. Also, its approach to modeling scattering is just superior. And it also has a more obvious scheme for including discrete structures like H2 regions. But at the end of the day, yeah, it's bias. Okay. So over the next few years, we're also poised to benefit from new parallax programs and optical and radio ISM surveys. So there are a few different VLBA parallax programs that are currently ongoing and will give us even more parallax distances to pulsars for our model calibration. I'm also actively working on using data from the SDSS-5 local volume mapper, which is a large integral field spectroscopic survey of the galactic plane. And what I'm trying to do is essentially cross-correlate LVM measurements of densities based on optical line diagnostics with pulsar and FRB measurements. And then in the next few years, roughly 2027 to 2028, we will see the advent of DSA 2000, which is essentially the next big radio survey in the US. So DSA 2000 is an array of 2,005-meter radio dishes. It's going to be located in Nevada. And DSA 2000 is going to be doing an all-sky radio imaging survey that is anticipated to discover tens of thousands of new pulsars and FRBs. And so when we enter the DSA 2000 era, I think we are going to take one step closer to actually trying to do true tomography of the ionized ISM with pulsars. We are not there yet by far, but I think in the next few decades we will move there. And DSA 2000 will be our first step in developing tomographic methods based on pulsar DMs. Okay, so with that, I will leave you with the summary and happy to talk more.
Okay, I've got quite a few questions, and I'll ask more.
So there is a recombination time depending on the density of those H2 regions, and in principle you can see time dependence of those things if the density is high enough, because the recombination time is for the, I don't know, 100,000 years, the mean density of the ISM, but could get down to 10 years, I guess, in a very high density region.
Yeah, that's an interesting point, and actually a project that I didn't get to mention is that we're actually looking at variations in DM over time of pulsars behind H2 regions. There's actually a grad student visiting Caltech right now who's working with me explicitly on this. So we're looking for it. Well, we see variations in DM, but the difficulty is in determining whether those variations are due to the foreground H2 region or due to something else. Because even for pulsars that aren't behind H2 regions, we generically see DM variations. And that's because pulsars are moving at hundreds of kilometers per second through the ISM, so we can see changes in their density on timescales of weeks to months. And that's just a generic feature of the fact that they're probing different lines of sight as they move. So the interpretation is non-trivial, but yeah.
Do you see variations in the scintillation arcs? Because if they're like tiny structures, maybe the timescales also.
Yes, we do, yeah. So it depends on the line of sight. There are some pulsars for which we see the same arcs persist over decades, and then there are other pulsars where we see features that change over timescales of months to years.
Yeah.
Hi, Stella, great talk. Are you familiar with the work by Lewis McCallum with Ken Wood and Bob Benjamin on
Yes.
lighting up our local 3D dust? Yeah, I mean,
Yeah.
I've been impressed how good that looks for things within a kiloparsec. Obviously, for things further away, you still need all these other constraints.
Yeah, I was impressed by it too. So Bob came to Caltech last fall, actually, and we had a great conversation about it. And we are hoping to work on a follow-up project to that paper, which will actually compare the H-alpha mass that they're generating to pulsar measurements. So I think it's a very promising technique, and I'm eager to see where it can go.
Yeah, that's one of those things where I wish I had thought of it, because it just works much better than I expected it to use.
Yeah, it is surprising.
Seems like that'll be a key to getting the nearby stuff right.
What's the method?
So you know this Edenhofer et al. Dust map that we worked on when Cordia Edenhofer was here a couple of years ago, 3D dust map going out to 1.25 kiloparsecs. And if you just say dust is gas, place a bunch of O-stars in it, light up the gas.
O-stars whose
ionize
positions
it.
we actually
Yeah,
know.
O-stars whose positions we actually know. And then ask what the electron density in the H-alpha ferment would look like and put it next to the H-alpha map. The agreement is shockingly good. That's a chain of assumptions that are so reckless that I would never expect this to work, and yet it kind of works. So I think they're onto something, and I'm very excited about that, and I'd like to see how it meshes with what you're doing.
Yeah, I agree completely. And I think if we can have a more robust model of local ISM features within a kiloparsec based on other tracers, that potentially helps reduce a lot of degeneracy in the calibration of these galactic scale models, because it turns out there's a fair amount of fine-tuning to get your model to work for a combination of like local bubble plus gun plus all this other stuff with things that are much further away. It's a very difficult problem. So if there's some way we can just anchor the model within the local ISM, that might help us a lot.
Yeah, and we're continually refining the 3D dust maps too.
Yeah.
So,
Yifei, did you have?
Yeah, it's about the turbulence. You mentioned turbulence, and in fact, turbulence was controlled by many parameters. And apart from the power spectra and the other parameters will affect the final results. I just want to know what's the is there any degeneracy here? Because turbulence is very, very broad concept. Not just the power spectra, but also like the pattern, how this kind of dense cloud was assigned in space will also affect this kind of dispersion. So will it affect it?
Yeah, so the short answer is yes, right? Particularly for scattering, like the location of where, say, a discrete structure is can have a dramatic effect on the scattering that you observe if you're assuming that the scattering is coming from that discrete structure. So like locations along lines of sight are very important. And yeah, so as you say, this is part of the overall like problem is how do you combine these different physical parameters like location with strength of turbulence in the screen, et cetera. Yeah.
This was really impressive, and I have many questions. Maybe we should talk about models, but I have two questions here. Maybe one comment first. We have already seen the shrinking of ultra-compact H2 regions. So just like Barry Keto has predicted, and David Wilner here at the CFA has worked on that with Christy Cree and using our models at the time. So I think this is seen, however, it will be super hard to find a sideline to one of your objects in these ultra-compact H2 regions. So I think on the large ones, timescales are larger than what you would have. The second one is a different question to what Doug has. I'm wondering about the galaxy at large and where you get data from. I mean, there is the High-Gal survey of bubbles, right? There is the Thor H1 survey that provides very high resolution of 21 centimeter plus additional stuff that has to do with ionizing gas. Is this something you can easily ingest in your model and use these data as constraints, or how do you go about these many surveys that are on the market?
Yeah, so the short answer is it's not easy, and at the end of the day we have to make some choices. So for example, for the H2 region cross comparison, I was mainly using catalogs that were based on radio and IR measurements, which are sensitive to H2 regions in principle across the entire galactic disk. Moving forward, say with LVM, we do have this question of like dust extinction and how deep into the plane you can reach. So, you know, I don't have like a great answer for you other than that one of the main tasks is just assessing all of the various data sets that are available and then determining which of these give us the most unbiased view of the ionized gas distribution. Because of course, when you're converting between different phases, you have you know, a number of parameters that come up, like what is the uncertain ionization fraction of the gas. And with pulsars and FRBs, you really are just sensitive to free electrons. So they are, in some sense, the most unbiased tracer of the electron density, but on the other hand, they don't give you any information about the phase of the gas, which makes it very difficult to compare to other wavelength tracers. So that's a roundabout way of answering your question, but it's something that we are constantly thinking about.
Okay, very quick last question.
Last question. If you take all the H2 region DMs out, do you know what the underlying distribution would look like? Would you see a smooth galaxy as opposed to one with spiral arms or other things?
Yeah, so it's really hard to say. I mean, if you look at the distribution of, say, DM, I mean, this isn't a great plot of this, but you can see some evidence of spiral arms in here, and it largely arises from asymmetries between negative and positive galactic longitudes. So overall, you can see that there's this large-scale asymmetry between negative and positive longitudes, and we think that is due to just the general spiral arm structure, and that isn't necessarily corroborated by all of these H2 region intersections, so it's very possible that there's some underlying kind of more diffuse component to the spiral arm density structure. But beyond that, it's hard to say, at least based on the pulsar measurements alone.
This would be a warp process.
Yeah, I'm really interested in thinking more about galactic warp. I don't know if we see evidence for it in our data yet. We also don't see any evidence for like a bulge, say. So I think as the number of total known pulsars increases, we're going to see many more of these interesting features. Right now, we're still kind of, you know, at the edge of dealing with a limited data set.
Alicia, is this very quick last question?
Oh, I'm going to talk to Stella later, but basically the question is, given all these other questions about looking at other data, I have a question like, have you done the very straightforward thing of just looking at super deep optical images of the lines of sight of the nearby things to see whether there's anything interesting, like these, bow shocks and clumps and clusters of stars and things that would have the small scale structure that you need to make it turbulence plus something else.
Yeah, so we've mostly looked at survey scale data, like say WAM, for example. I haven't gone yet to the point of like pursuing dedicated optical imaging of specific lines of sight, but I think that could be a really
The
fun
crazy thing
thing
is
to
I was in this
pursue.
call that Doug is very sorry that he missed this morning with Lewis and Bob Benjamin and Kenny. And we were looking at the DCAPS2 data, super zoomed in at particular lines of sight. And
Cool.
it's kind of incredible, Doug, thanks. So anyway, later, when you were
Yeah, let's talk more
look
about
at
it. Yeah.
Okay,
Cool.
that's,
That's a
thanks
super-
again.
Amazing.
And see you
Thanks, it was great.
in less than half an hour.
So